So good evening, everyone. I'd like to welcome you to Argonne National Laboratory. My name is Stephen Streifer. I'm the Deputy Associate Laboratory for the Physical Sciences and Engineering Directorate, which is the part of the laboratory that houses our High Energy Physics Division, which of course is very important for tonight's subject. So about 3 months ago, I was sitting in my office, and these two guys came to see me, Rik Yoshida and Jimmy Proudfoot. And I don't know if you've ever seen a kid at Christmas who was so excited that they were literally vibrating. So Rik and Jimmy came to see me, and they were like, something really, really important is going to be announced. We really have to make sure that we're there for the announcement. And they were right. On July 4th, there was an announcement from the two detector collaborations at the CERN High Energy Physics Laboratory, marking the announcement that a Higgs-like particle had been found. And of course, on July 4th, this discovery was so important that cities across the United States celebrated with fireworks. So it did get everybody's attention. The excitement over this discovery has actually continued across the world. As a matter of fact, University of California at Berkeley had just held a recent panel discussion on the Higgs, and the auditorium was so crowded that they actually had to call on the fire marshal to clear the aisles. So this is still quite a lot of interest in the basic science community. But if you're not a physicist, a lot of us are left wondering, what exactly is all the excitement about? So we put together tonight's lecture to try and answer some of these questions and to give a flavor of exactly why the Higgs particle, the Higgs boson, is such an important discovery. What exactly is it? Why is it so unusual? What's unique about it? And what's made it so very, very difficult to find? So these seem like fairly straightforward questions, but the answers to them have involved many people working for many years and an investment of billions of dollars in essentially the most advanced experiment that I think the human race has ever been able to see. Because the answers to these questions are really difficult to find out. But at the end of the day, the information that we gather about the Higgs boson is important because it's fundamentally linked to everything that we know about the universe. From the tiniest particles that make up matter all the way to the massive clusters of galaxies that make up the universe. So tonight, my colleague Rik Yoshida from High Energy Physics here at Argonne is going to try to give us a flavor of exactly what's going on in the community and why this is such an exciting and important discovery. Rik is a very renowned physicist. He currently works, again, in the Argonne High Energy Physics Division, and he is a member of the team that works on the so-called ATLAS detector at CERN, which is one of the collaborations that was involved in the discovery that we'll be discussing tonight. He's an expert in a variety of high energy physics areas, including the Higgs searches that you'll hear a little bit about tonight, and also in other topics such as electroweak physics, quantum chromodynamics, proton structure, and high-energy physics experimental techniques. He's worked on quite a number of experiments, both at Fermilab at Argonne and around the world, including Decay Lab in Germany. From 2003 to 2005, he served as the scientific leader of the ZEUS experiment at DESY in Germany, and that is the German electron synchrotron. He served on many scientific advisory committees, including the panel for high energy physics as part of the DESY laboratory. He's a fellow of the American Physical Society, and he holds both bachelor's and PhD degrees from Northwestern University, so he's been a local boy for a while. I look forward to hearing what Rik has to say about this topic, and I invite you with me to welcome Rik for being brave enough to try and explain this to us. So please, Rik.
Thank you, Stephen. So, Higgs boson discovery. So, it's been a very exciting year for those of us who do this kind of research. So, Homer's excited, dogs are excited, cats are fascinated. We have a lot to cover. We should get going. Okay, so the first part is called the mystery of the Higgs boson, in which we actually try to understand what the Higgs boson actually is. So, the Higgs boson is really central to our current understanding of our universe. So that means we really need to understand all of what we call modern physics. So that's the E equals mc squared atoms kind of stuff in order to understand the Higgs boson. And then in order to understand modern physics, you really kind of need to understand classical physics, which is the 17th century powdered wig kind of physics. Now, we're going to do that in the next 20 minutes, okay? And then we'll talk about the Higgs boson. But first, the electric car. Okay. So you may or may not know that the battery technology that's in Chevy Volt was largely developed here at Argonne. And this came to my mind because I found this picture when I was researching for this talk, and this is Benjamin Franklin flying a kite in a storm. Now, I hope you know that you're not supposed to do this, right? I mean, he was very lucky to escape alive after this experiment. But the interesting thing about it is, first of all, he has an assistant, apparently his son, and he's holding this little jar. And this jar is a device called Leyden jar, and it's an early battery. So what Franklin was trying to do was to charge this battery with lightning. So why did he want to do this? So in the 18th century, electricity was a kind of a parlor trick. So what you could do is you could use something like a Leyden jar. You could charge it with this device, which generates static electricity. Charge it, here's a Leyden jar, and make a little spark like this, and that would be the entertainment for the evening. Now, what Franklin wanted to find out was whether this little spark is really the same thing as that thing you saw in the sky. Are these really the same things? So he was asking a very fundamental question, right? So sometimes practical usage of such a fundamental question takes a very long time. So as I said, in the 18th century, it was really a parlor trick. There were early attempts at making these things practical. They thought that this might cure paralysis. Here's the Leyden jar. It's a lady getting treated. In fact, Franklin tried this and debunked it. But eventually, you might arrive at a practical electric car. So the moral of this little story is that there are cats, curious cats, who wonder what's going on, and there are practical cats who are mainly interested in where his mouse is coming from next, rather than a quantum theory. But the curious cats often precede the practical cats, and tonight's story is really about the curious cat. But I brought up electricity for a reason. So in the 19th century, there was a man named Hans Ørsted, and he noticed the following thing. So if you put electric current through a wire, then it would deflect a compass. So what's happening here is that the electric current through this wire is generating this magnetic field, and it's attracting this compass needle. So basically, it turns out that electricity and magnetism is part of the same phenomenon. Right? So through these studies, people realize this, and this is the thing called electromagnetism today. So later on in that century, there was a man named James Maxwell, and he figured out the following thing. So now if an electric field is inducing a magnetic field, and magnetic field is inducing an electric field, then this thing can actually propagate in space like a wave. So there's a little pictorial representation of such a thing. So you have an electric field and a magnetic field alternately being propagated as a wave. And the amazing thing is that this wave turns out to be nothing but light. So the light that you see around us are electromagnetic waves. Now, around the same time, in the 19th century, there was a physicist in Germany called Heinrich Hertz. He was looking at something called photoelectric effect. So it turns out that if you shine light on certain kinds of metal, like lithium, for instance, then you can pop out electrons from the metal. But there was something funny about this particular thing. So sometimes it wouldn't happen, and if it didn't happen, it didn't matter if you increased the amount of light that you shone on it. It still didn't happen. But if you changed the color of the light, it would happen. And this is a little bit funny, you see, because if it takes a certain amount of energy to pop out electrons, then you would think that more light, more energy would help, but it doesn't. You have to change the color of the light. So no one could answer this for a long time until this guy came along. So this guy was working in a Swiss patent office, and he said, well, this would make perfect sense if light were particles called photons. So, and the energy of these photons determine the color of the light. So if you have blue photons, it has enough energy to knock out electrons out of atoms. But if you have yellow ones, it doesn't. So it doesn't matter how many more yellow ones you have, it never works. Okay? So this all made sense, but then we have this problem. we just said particle is a wave, this light is a wave. And now we say light is a particle. What the heck, which is it, really? And the answer turns out to be yes, it's both. And it's quantum theory, quantum mechanics. And as you may be aware, that quantum theory is one of the weirder things in modern physics, and it's rather difficult to understand. And here's Niels Bohr, one of the founders of quantum theory, and he had this to say about it. I guess he was arguing with somebody. He said, but if anybody says he can think about quantum theory without getting giddy, it just means that he hasn't understood it properly. So it's difficult, but we're going to understand it in the next 2 minutes because we don't have much more time than that, okay? So, okay, particle is wave and wave is particle. What does that mean exactly? So you know what a wave is. A ripple in water is a wave. So if you have two ripples in water, you know that they interfere. If they go up at the same time, then they add up. And if one goes down and the other goes up, they cancel each other out. There's an interference. Okay? So there's a classic experiment to show this, and it's called the two-slit experiment. And what you do is you create a wave behind a wall with two slits in them. So the wave moves towards the wall, goes through the slits, turn into two waves, and they interfere with each other. So if you look at how much wave there is behind this wall, and it turns out there are places where they add up, like this, and there are places where they cancel each other out. So you get this stripy pattern. This is characteristic of interference. Okay, now, let's see what happens. Let's think about what happens if you do this with particles. So you would think that if you have a bunch of particles moving towards this wall with two slits, some of them would make it through, and others won't. If you make it through, it would just go right straight back to the wall and hit the wall, so you have these two bands right behind the slits. Now, indeed, this is what happens if you use paintballs or something to do this, but it turns out that if you do it with the electrons, they actually interfere. So electrons, even though they're particles, they're waves, quantum theory, so that it actually sort of goes through both slits and interfere with itself and decides that it needs to interfere and end up in this kind of stripy pattern. Now, unless you're an extremely gullible person, you should be asking to yourself, how could that be? How could a particle be a wave? So bear with me for a moment. I'm going to talk about something slightly different. So if you are a man in a buggy on a horse, and you're moving around, and your activity radius is 1 mile, and if you were to go up to him and tell him that, the Earth is round, it's a sphere, he would say, that doesn't make any sense. How could it be round? I would fall off the edge. It doesn't make any sense. But to a man who's orbiting the Earth 10,000 miles away, Earth is manifestly a sphere, right? So the question the man in the buggy should have asked is not how can the Earth be round, but how can the Earth be round and that I have not noticed? How could that be? That's the question. So it's the same thing here. The question is not how could particles be waves. This is an experimental fact. But the question is, how could particles be waves and we have not noticed? And the answer is basically the same. So the smallest particle that you see every day, let's say a grain of sand, has very little wave characteristics, so little that you would never notice it. But if you go 1 billion times smaller and you start looking at atoms, those things are definitely waves and particles at the same time. Okay, so that's quantum theory. So once you get this far, things actually get a little bit simpler in some sense. So here we're in a position now to actually understand the basic interaction of electromagnetism, what's really happening. So this is called quantum electrodynamics, or QED, and this was figured out around 1945. So let's say you have an electron moving along. You have another electron moving along. And electrons are charged, so I indicate that by this minus sign. So they have to interact with each other there because they're electrically charged. So that means they have to somehow exchange information between them. So how does it do that? So in the very fundamental sense, what it does is exchange a photon. Now, we think that all forces can be described in this way as an exchange of some kind of a force carrier, right? And the photon is the force carrier of the electromagnetism. So this is the very basic interaction of in electromagnetism. Now, physicists draw these kinds of diagrams all the time. We do it slightly different, so I'm going to show you one. So it usually looks something like this. So solid lines here are electrons. It's indicated by E minus as electrons. This is the other one, and here this thing is the exchanged photon. And these things are called Feynman diagrams, after the guy who invented it, Richard Feynman. You may have heard of him. And the amazing thing about this diagram is that this is completely equivalent to writing down the rather complicated mathematical expression that actually describes this interaction. So these lines and points and things actually correspond to mathematical formulas, and it's really correct in that sense. So we can use these things instead of formulas, and we're going to do that later on in the talk. Okay? So we're going to wind back the clock about 50 years. When people first discovered atoms, people thought that these things just basically last forever. But it turns out that they decay, and this was figured out by many people, including Marie Curie, around 1900. So there are many ways in which atoms decay, but I want to talk about something called beta decay. Okay, so what's happening here is that, for example, cesium atom is decaying into a barium atom and giving off some particles. So what's happening inside the atoms is, in this case, is that there is a neutron, and there's a proton, which is turning into a proton and giving off an electron and a neutrino. Now, you probably know what an electron is. You might not know what a neutrino is. A neutrino actually is a very interesting particle which has its own very interesting story, which I really don't have time to go into for the moment. So we're just going to have to leave it today as another elementary particle. Okay? So, but this was a brand new interaction. Nobody had ever seen anything like this. So this was not electromagnetism. So it was something else. And this was called weak interaction because it didn't happen very often, basically. It didn't decay. Atoms don't decay all the time. This doesn't happen all the time, so it has a weak interaction. So discovery of radioactive decay leads to the discovery of weak interaction. And it's very tempting at this stage, then, to put this particle here as a force carrier of the weak interaction, just the same way in which the photon was a force carrier of the electromagnetic interaction, and we call it the W boson. And boson, we're getting close, right? Right. So W boson is the force carrier of the weak interaction. So now comes the next question. Now, we found out in the 19th century that electricity and magnetism are the same things. So what about the weak interaction? Is this really the part of the same thing? So if I look at this diagram and that diagram, they kind of look the same, but there's a big difference. So the force carrier of the electromagnetic force is massless. It's a photon. It has no mass. It zips around at the speed of light all the time. Whereas the force carrier, the W boson of the weak interaction, has to be heavy. In fact, it has to be heavy as a silver atom, which is 100 times heavier, more or less, than a proton or neutron. The reason it has to be heavy is if it weren't heavy, it would be very easy to produce, and if it were easy to produce, then atoms would actually decay all the time. And life, universe, and everything would not be the same the way we would actually find it. So it has to be heavy. All right, but that's actually a big problem, it turns out. So it turns out that if you have a massless force carrier, this is mathematically okay. So the science guy says it's okay. But if you have a massive carrier, somehow, this turns out to be mathematically not okay. Now, to be honest, it's actually okay, but it's just very, very nasty. Once you have this, then all sorts of bad things happen mathematically. So the problem seems to be with this mass thing, right? So let's figure out what this mass is. We can do it together. So you know that things are made of atoms. And some things, like lumps of gold, have masses proportional to the number of atoms in them. So you have another lump of gold with twice the number of atoms, it weighs twice as much, right? So the mass has to do with something to do with the mass of atoms, a number of atoms, right? But different atoms have different masses. So, but if you look inside the atoms, atoms are made up of their electrons, but those are things that are very light, mostly made up of protons and neutrons. So if I count the protons and number of protons and neutrons, atoms, the masses of atoms happens to be basically proportional to the number of protons and neutrons, almost. So mass has something to do with the number of protons and neutrons, must be. But then these days we know that the protons and neutrons are made up of other particles called quarks. And here we run into a little bit of a problem in this argument. So because quarks, it turns out, are very, very light. In fact, it's so light that it doesn't make up the mass of the protons and neutrons. But we're okay because this guy says it's okay. So he's a little bit older now, but it's the same guy. And he says E equals mc squared. What does that mean? So E is energy, m is mass, and c is speed of light, which is 671 million miles per hour. So this formula tells you that energy is mass times something very, very large. Okay? And so it turns out that the quarks inside the protons are held in place, but with an enormous force, so that the proton actually holds an enormous amount of potential energy. And this is a new force that we haven't talked about. It's called the strong force, and its force carrier is called the gluon. It all sounds very interesting, and I'd love to get into it right now, but we have to move on. So we just have to leave it like this, that there's an enormous force inside the proton, and that energy is the mass that you see all around us. That's mostly what it is. But we still have a problem, because we said quarks have mass. And quarks don't have internal structure. They're not made up of anything, but they have mass. A little bit, still have mass. What about the W boson? The W boson has no internal structure either, so that has mass. So where does that mass come from? So that's where Peter Higgs comes in. So I should say here that 6 people working in 3 different teams actually came up with basically the same idea at the same time around 1964. And I'm just using Peter Higgs as their representative, okay? But Peter Higgs says the Higgs field is everywhere. He didn't call it Higgs field, but anyway, very modest man. So hang on a minute. Before we talk about it, I think we have to understand a field a little bit better. So I've been saying words like electric and magnetic field without really telling you exactly what that is. But here now we have to actually understand what a field is. So we're going to do that using gravity. So you know that an apple feels the gravitational force of the Earth. Now, but I can think of it another way. So I can think of it as Earth generating a gravitational field. And that means that any point in space has associated with it force or acceleration, really, but something that gives you that force. And if you put an apple at that point, it's going to feel the force that belongs to that point. If I put it over here, it's going to feel the force that belongs to that point. Okay? Now notice I didn't say anything really different. I just said it in different words. But once I have this concept of this field, then I can do the following thing. So I can draw, for example, the gravitational field of the Earth and the Moon. I can draw the gravitational field of the solar system, the galaxy, the cluster of galaxies, and so on and so forth. So I brought along an expert to explain what a gravitational field is. Here he is. He says, the force, that's not it. So the gravitational field is an energy field created by all things. It surrounds us and penetrates us. It binds the galaxy together. That's a fine definition. So a field has some action property. It doesn't have to be force, but some action property associated with points in space. It's really space-time because we need relativity, but I'll just skip over that for a moment, okay? So where were we? There was Peter Higgs, and he says the Higgs field is everywhere. Now, the action property of the Higgs field is to give mass to elementary particles. So here is a picture of the Higgs field. It doesn't look like anything, it's empty space. So if you're light, if you're a photon, then you zip along because you have no mass. You don't see the Higgs field. But if you're an electron, then you see the Higgs field, you have to interact with it. That's indicated by these crosses, and you gain mass. And if you are a W particle, then you interact more, and you gain heavier mass. Now, remember our mathematical problem. It turns out that if you introduce mass in this way, using the Higgs field, here played by Russell Crowe, everything turns out to be okay. So here's our friend, the W boson, and the photon, and because the W boson mass is actually created because of the presence of the Higgs field, if you were to take that away, the W boson also turns out to be massless, and in fact, it's a long-lost cousin of the photon. And in fact, it turns out that electromagnetic and weak interactions are really part of the same thing. So at this point, even a nasty Roman emperor has to agree that this is okay. Right, so here he is again. What is the Higgs field, Obi-Wan? No. The Higgs field is what gives elementary particle its mass. It surrounds us and penetrates us. It binds the universe together. This is a very handy quote for anything to do with fields, actually. So, and reveals, actually, that the electromagnetic and weak interactions are one and the same. So, this explains everything, right? All makes sense now. But some of you may be saying, wait, that's how it really works? There's some magical field that makes everything okay, and now you've got everything fine? Is that how it works? So what about that, Professor Higgs? So he says, I see you don't believe me. To convince you, I will make a prediction. 1964. He was a little bit younger then. So there are waves in the Higgs field, just in the way that there are waves in electromagnetic fields. Our friend might say there's a disturbance in the Higgs field. Now remember, this is quantum mechanics. Waves are particles. So there's a yet undiscovered particle called the Higgs boson, which is a wave in the Higgs field. If you find this, then we'll know that all of this is true. So then we ask, where shall we find it? So what's the mass of the Higgs boson itself? And actually, he doesn't know. Yeah, now it turns out that he actually knows absolutely everything else except the mass, but the mass he doesn't know. So this brings up to part 2, which is the hunting of the Higgs boson, in which we ask, how do we find the Higgs boson? So how to find the Higgs boson in 3 easy steps. You collide some protons at high energy. Energy turns into matter. Remember, E equals mc squared. And then the Higgs flies out, and we find it. So there's some kind of a bang. There's a whoosh, and the Higgs comes out. Okay, I skipped a few steps here. So in order to go into a little more detail, I'm going to have to talk about units of energy and mass. So this is going to be a little bit dry, so bear with me for a moment, okay? So remember, E equals mc squared, so energy and mass is the same. When we say energy, the mass, it doesn't make any difference. We usually use it interchangeably. So if you hook up a 1-volt battery to 2 metal meshes, and you were to let go of an electron on one end, by the time it gets to the other end, then the electron has a kinetic energy of 1 electron volt. Okay. So if you were to do this 1,000,000 times, then that electron would have an energy of 1,000,000 electron volts, or 1 MeV. If you do it 1,000,000,000 times, then you would have an energy of 1 giga electron volt, or 1 GeV. If you do it 1,000,000,000,000 times, you would have an energy of 1 tera electron volt, or 1 TeV. Now, in terms of mass, electron mass is about 500,000 electron volt, half MeV. proton has a mass of around 1 giga-electron volt, or 1 billion electron volt. And our friend W boson is 80 giga-electron volts, so 80 times heavier than the mass of the proton. And the Higgs, the unknown Higgs in 1964, could have had its mass as high as 1 tera-electron volt. Now, I just said very big numbers now. And if you don't work with these kind of numbers, it's very hard to get a feeling for what these numbers mean. So here is a pile of million pennies next to a man. Here is a pile of 1 billion pennies next to a man. And 1,000 of those, this big pile, would be 1 trillion. So if a penny were an electron volt, that would be a million electron volt, or MeV. That would be 1 billion electron volt, or GeV. And that 1,000 of those would be a TeV. Now, a TeV sounds like an enormous energy, and it is in some ways, but it isn't in other ways. So a TeV is the kinetic energy of a flying mosquito. Now, mosquitoes are made up of molecules, which are made up of protons and neutrons, and there turns out to be something like 1 billion trillion protons and neutrons in a mosquito. So if you're keeping track of your billions and trillions, then you'll know that each proton in the mosquito has a kinetic energy of 0.00000001 electron volt, or 1 billionth of an electron volt, so very tiny amount of energy. So in fact, you can think of a mosquito, or even yourselves, as a proton accelerator, but it does it not so well. So in fact, the mosquito-mosquito collider is out as the machine to find the Higgs. So we use instead the Large Hadron Collider, or LHC, which is located in Geneva, Switzerland. Here's an aerial photograph of it. So it's about 300, 500 to 500 feet underground in a tunnel. The inside of the tunnel looks like this. And the diameter of this ring is about 5.5 miles. You can see the Geneva airport to give you a little bit of scale. So the Large Hadron Collider accelerates protons to 4 TeV, and then they collide them head-on, so there's 8 TeV of energy available to look for new phenomena. Now, this machine has a mission to explore the frontiers of particle physics, and this includes the Higgs boson. It does many, many other things, which I really don't have time to tell you today, so we're going to just stick with the Higgs boson for today, but it's not the only thing by far, not the only thing that LHC is built for. So LHC collides 100 billion protons with 100 billion protons every 50 nanoseconds. So what's a nanosecond? So a nanosecond is 1 billionth of a second. So light, which, as you know, goes 671 million miles per hour, travels about that much in a nanosecond. Now, you may think that this is a very small amount of time, but actually you use it all the time. If you have a smartphone or a computer, very likely you'll have a processor inside those machines which are clocked at 1 gigahertz. That means that that thing is actually doing an operation every nanosecond. So a nanosecond is a kind of time, even though it's tiny, that humans can actually deal with these days. But the Higgs boson, on the other hand, lives for about, after it's created, lives for about 10,000th of a billionth of a nanosecond, which is already a billionth of a second. So basically, this thing is created, and it goes poof and turns into something else. So it's not good enough to produce the Higgs boson. We have to be able to see it. So that's where the detectors come in. There are 4 main detectors at the LHC. So this is the LHC tunnel underneath the thing, and you see 4 different detectors. 2 of them are actually not made to detect Higgs boson. They do other kinds of physics. So we're not going to talk about those today. There are 2 that do, and they're called CMS and Atlas. The ATLAS experiment apparatus is 7 stories tall. You may be able to make out tiny people there. And it's weighs about 7,000 tons, and it's a very complicated machine. And it was built with more than 3,000 physicists, engineers, computer programmers from 174 institutions from 38 countries. When I say institutions, that means universities, laboratories like Argonne and so on. About 20% of this collaboration is US, and Argonne has been part of this experiment since 1994, so we've been doing this for almost 20 years. CMS is kind of similar, so the makeup of CMS is rather similar, and US participation is also similar, and Fermilab in particular is a participant in the CMS detector. Now here's a picture of the detector under construction. You may be able to make out the tiny people down there. A large portion of this detector is built right here at Argonne, just down the street, and here's a picture of this portion that was being built into the big detector. Now, how this thing works is an extremely interesting thing, but I'm afraid we have no time for that because we've got to move on to the discovery of the Higgs boson. Okay, so if you were able to talk to the Higgs boson, he might say something like this. I don't always appear after a proton collision, but when I do, I decay almost immediately. So you might ask a follow-up question. How often do you appear after a collision at the LHC? And the answer turns out to be once every billion times. So remember the pile of billion pennies. We're looking for 1 penny in that pile of billion pennies. Let's get a better handle on this. So what particles do decay to? Well, he says it depends, but I just decay into those particles that you know. So it turns out that the Higgs particle sometimes, actually very seldom, but sometimes decays into 2 photons. So there's a bang and 2 photons come out. A lot of other things come out, but photons come out. Okay? So since we're all experts with Feynman diagrams, here's the Feynman diagram. And this is the Higgs boson. Something complicated happens in the middle, and there's a photon coming out and a photon coming out. So that's how it works. But the problem is that there are other things that produces 2 photons. Here's another Feynman diagram. So this is 2 quarks. This is one, and here's the other one, getting together to produce 2 photons. Now remember, protons that we're colliding are made up of quarks, so these things can happen. But it turns out to be pretty good, actually, because there's one of these for every 300 of these. So now the odds are better. Now it's not 1 billion to 1, it's 300 to 1. So this is something we can manage, but we still have a problem because I don't know when you see 2 photons whether this really happened or something else happened, right? So now we need to have some kind of a fingerprint of the Higgs boson. This is where the detectors come in. So detectors can do something called mass reconstruction. So what the detectors are able to do is to measure the energy and the flight path of these photons, and from this you can reconstruct the mass of the particle from which it came from. So if you do this with a Higgs boson decay, then you would reconstruct the Higgs boson mass. But if you do it with this other thing, which as you see doesn't really come from a single particle, then you kind of get a random mass. So let's make a plot. So here's a line, and along this line are masses. Okay? So let's say we find 2 photons coming out, and then we reconstruct the mass. I want to put this on this line, so I put it there because I measured it there. And I do it again, and again, and again, and it's mostly random because most of this is random stuff. Right? But eventually, things may begin to accumulate in certain places because every 300th time it ends up in the same mass, the Higgs boson mass. So what we need to do is to look for a bump in this mass spectrum, so as we call it. So in fact, on the 4th of July, the Higgs boson discovery was announced. And so the 2 experiments, CMS and ATLAS, looked at this mass spectrum and found this. So ATLAS found this, and CMS found this. And those bumps, they're the Higgs boson. That's the Higgs boson. They're both at the same place. And this is the Higgs boson. So we also found, actually, not only this decay, but other decays. So Higgs boson can also decay into our friend, the W boson. We were able to find these as well. And it could also decay into something called the Z boson. The W boson, you know, Z boson is another cousin. Okay, so there was a lot of celebration. People hugged. There were magazine covers were about Higgs boson, and even Dr. Seuss was excited. So let's take stock for a moment and look back a little bit on what we just discussed. So this is somehow a culmination of all these people doing things and thinking things and doing experiments, and there are many, many more who are really crucial in finding the Higgs. And I went back as far as the 18th century, but obviously it goes back through the ancient civilizations to the first guy who looked up and asked, what is going on here? So the Higgs discovery is actually the completion of what we call the standard model of particle physics that explains all phenomena we've been able to examine closely. So as such, it's a big achievement. However, in the last 20 years, things that we can examine closely have actually expanded a lot. So people can now examine closely things like supernovas, rotation of galaxies, and cosmic microwave background. And from this, a pretty amazing picture of the universe has emerged. So it turns out that most of the universe is made of energy and matter which we know nothing about and is designated as dark. And the things that we understand, the ordinary matter is only a few percent of the universe. So in fact, the standard model of particle physics describes that ordinary matter. So we're very, very far away from understanding everything, obviously. So like this guy, we might say Higgs boson discovery is not the end. It is not even the beginning of the end, but it is perhaps the end of the beginning. So indeed, the LHC experiments were built to look for dark matter, and that's one of the things that we're doing. Now, I'm basically done, but I have a few more things to say in the epilogue about the fundamental science. So in forums like this, we're very often asked, what is the practical use of the Higgs boson discovery? And the answer is, we have not the slightest idea. This is completely unknown. If somebody tells you different, they're just not telling you the truth. So the obvious question is, why do this kind of research? For those of us who do it, it's really a pure quest for knowledge. Then the fair question, of course, is, what is the value of this research to community? So the fundamental research uncovers fundamental principles of nature, and having uncovered fundamental principles of nature, that lets us make improvements in a very fundamental way. So this is what I was trying to get at with this Franklin and Chevy Volt example. But perhaps maybe there are other examples which are even better. So if you wanted to improve a communication network, you might invent a Pony Express without any knowledge of, which doesn't require any knowledge of physics. But if you wanted a global communication network, then you'd have to know quantum theory as well as many, many other physics things. And in fact, if you didn't know the fundamental physics, you would not even think that such a thing is possible. We live in a world where we pick up something out of our pockets and call and expect to call halfway around the world. And this is an amazing thing. So, but then you might ask, what about the shortest term? After all, 18th century to 21st century is kind of a long time. But what we do in high energy physics and similar fields is we ask very impossible questions. We ask things like, what is mass, or what is time? And in order to answer these questions, we actually task ourselves with impossible things. we want to collide 100 billion protons together with each other for every 50 nanoseconds. We want to find a particle that's produced every billionth time. And in doing this, we push the envelope of technology. So just to give you an example, these are biological tools which were developed as a result of the LHC detectors. In fact, this is from the Atlas detector. And you may know that the World Wide Web protocol that you probably use absolutely every day was invented at CERN just to solve the problem of communication between scientists around the world. And there are, of course, medical accelerators now in many, many hospitals. So I'm at the end. So scientists, you may think of us as those guys in lab coats with the answers, and we do have some answers, but we really think of ourselves with the guys as the guys with the questions. Okay, thank you very much.
So thank you very much, Rik. Before we take some questions, I was asked to mention that there's some intellectual property lawyers that are right outside that'd like to have a few words with you. So I'm sure that there are several questions in the audience that Rik would be delighted to answer, and we have a few people wandering around with microphones because it's a big room and we'd like to make sure that people are heard. So I saw somebody over here with their hand up. So right here, please.
Yes, I was wondering if you could briefly describe the difference between the W and the Z and the Higgs.
Well, W and Z are both force carriers of the weak interaction. The Higgs, so what happens is that the Higgs field actually interacts with the W and Z bosons and turns them into massive particles. The Higgs itself is actually kind of an indication, Higgs boson itself is a kind of an indication that the Higgs field actually exists. If you like, you can think of it as kind of you don't know that air exists until the wind blows, and it's kind of a thing that you actually, it's a proof that actually exists.
So, right here, please. Gentleman in the tan shirt.
Do you think that Moore's law would apply to the development of the receivers for neutrinos?
I don't think I'm so competent to answer this particular question, but
Looking for the development of the neutrino development for receivers so that we can get rid of the satellites.
The neutrinos obviously have this very difficult problem that they don't interact with anything or hardly interact with anything. So that makes it very difficult as a means of communication.
We got that big box for the receiver on neutrinos, and it's huge and it's real expensive.
Yeah. So the reason we in order to study neutrinos, we need very big detectors. Okay. So the reason is that the neutrinos interact very weakly with everything. So that means that you need a lot of mass in order to find a single neutrino out of billions and billions of neutrinos, and that's why it's like that. You know, I think the communication, is very difficult using such a particle. There are probably better ways to do the communication than doing that. Yeah.
But it'll be interesting to see.
Can you explain why the Higgs boson is called the God particle?
Oh, please, go ahead.
Can you explain why the Higgs boson particle is sometimes called the God particle?
Yeah, I think this was a title of a book, and I think it was a kind of an attempt at popularization, probably a slightly unfortunate one. Well, yeah, Leon Lederman, who wrote the book, says he wanted to call it a goddamn particle, but because it was so hard to find.
We have only good taste to blame.
Yeah.
So here in the back, please.
Yes, I wonder if you could speculate on why different fundamental particles feel the Higgs field differently.
That's a very good question. And the answer is we don't really know. So there is no part of this theory that explains why different fundamental particles have different mass. And that is a big hole. And something that we think means that there must be something beyond it that explains all of this. And, but it's actually something that's very fun, very profound.
So please, right here.
This is a two-part question, kind of. We know that the Higgs particle, or the Higgs boson, has mass. Can you explain briefly, first of all, why it would split into the particles that it might actually split into, and how the Higgs boson that has mass can split into two photons that don't have mass? Right. It turns out that there are two different mechanisms by which the Higgs field gives mass. And one is for things like the W and Z bosons and actually the photon, it turns out, somehow the Higgs field gets entangled up with a weak interaction field. Whereas the fermions or the quarks, they really interact with the field. I'm not sure if you're asking what gives what the mass of the Higgs signifies, or what does it mean. So the mass of the Higgs is, as we discussed, it's very hard to pin down theoretically what it is, but it's a consequence of this field, which is actually, let me start again. Okay, so Higgs field is very different from other kinds of fields in that basically in the vacuum, most fields are on the average nothing. But the bizarre thing about the Higgs is on the average it's something. Once you have this kind of a field, it's the wave in it has to have mass, and that's what the Higgs boson mass is. And it's actually a fundamentally different kind of a vacuum than we have known before.
So right here, please.
There's a well-known anecdote. When Faraday announced the discovery of electromagnetic induction in the middle of the 19th century in Britain, the Chancellor of the Exchequer was there, and he asked the same question. Tell me, Mr. Faraday, of what use is this? Mm-hmm. And there are two versions of the answer that Faraday gave. One was, well, I don't know, but one day you will tax it. And we pay our electric bill tax every month. Yeah. And the second version, which is just as good but different, was, of what use is a newborn baby?
Mm. Yeah.
So the Higgs field gives mass to every particle. What gives mass to the Higgs boson? It interacts with its own field? How does it?
Yeah, well, there is something called the Higgs self-interaction, which actually does interact with itself. But as I said, its mass has to do with the way it manifests itself in the vacuum. So I can't explain it better than that for the moment. It's a little bit complicated.
Maybe I'll ask later.
So there's a question back here in the back.
How much data have you actually collected out of the 1 in 300? Like, how close are we to actually finding the mass?
Let's see. So this amount of data, so we know the mass of the Higgs boson to about GeV, so less than 0.5% mass as it is. Now, so by the end of the year, we should be able to, we will accumulate maybe 3 times more data than we have. So, in some sense, the mass will be better known. What we're actually interested in doing now is, you may have heard that this is called the Higgs-like boson discovery. And the reason it's called the Higgs boson-like Higgs-like boson discovery is because we haven't quite pinned down all the properties yet. It looks like the Higgs boson. It has all the right characteristics of the Higgs boson. Now, we would be very interested to know if there is a slight difference in this thing that we found than in the Higgs theory. That would actually mean that there is something that we don't understand, and that actually makes us very happy. If you don't understand something, that is very exciting.
Okay, so that's the next thing we're trying to do.
Since we found the Higgs boson and understand it's a field, is there a thought out there what would happen if we were able to manipulate the Higgs field?
Yeah, so the practical usage of the Higgs field. I have no idea, but Higgs has something to do with the mass. We don't actually understand gravity very well. So I don't know. Anti-gravity, spaceships, who knows? I have no idea.
There's one here and then one here.
When you say there are waves in the Higgs field, are there certain instances where a wave might a trough might cancel out a crest in a wave, and in a sense, give nothing, or is that
yeah? So
possible?
All of these particles that are waves, they act exactly like waves. So if there are two waves, they will interfere with each other, and those things are actually, built into the theory, and we can tell exactly how those things happen. So yes, they're waves, and they're real waves.
First, thank you very much. Excellent lecture. Should the Higgs be a boson?
Yes. It's a boson, that much we know. From the theory, it has to be a boson. It turns out the fact that it decays into 2 photons tells us that it's a boson.
Even with the unusual mass properties, the mass waves, mass fields, because it's so different from the other bosons?
Yeah.
Or should it somehow get its own subcategory?
So this is a peculiar particle. It's rather unique. And we know it's a boson. We know certain properties of it. And we're really trying to pin those things down. But for the moment, it really looks like the Higgs boson that we've been looking for. So.
Actually, I have one question down here, please.
Is the discovery of the bosons going to help us understand what happened immediately after the Big Bang?
After the
Big Bang.
Big Bang. Yeah, to a certain extent, yes. I mean, there are many, many mysteries of the Big Bang, but yes, the mechanism by which how the universe evolved involves the understanding of the Higgs field and how that works. So yes.
Do you think the answers you'll find out from the Higgs or other fundamental particles could help us understand dark matter and energy, or vice versa?
I'm sorry, I didn't quite.
Do you think the answers you get from understanding these fundamental bosons and particles could help us understand dark matter or energy?
Yes. Yeah. So the standard model itself has no explanation for dark matter. Okay. So there we have some clues, however, of finding dark matter, and we think we should be able to do this with an extension of the standard model. And this is something that we're actually looking for. Dark energy is a different matter. Different energy. That's much more mysterious, and I frankly couldn't tell you how people are looking at it, but I couldn't tell you how we're going to find out what that actually is. There's not a seminar in here or lecture in here someplace.
Yeah, I think I'll invite people back sometime in the future to hear more about that. So we did have, I think, one more question here in the back.
Yeah. Thank you for the lecture. You mentioned that the Higgs field is everywhere, right?
Yes.
Is it uniformly everywhere?
Yes. Yes.
Thank you.
Yeah, that's a. Yeah.
So let's take one final question. I think I saw a hand up right here.
These different particles you're talking about and all that, is that really just manifestations of string theory? I mean, how does that fit in? Are you really looking at something that you got to look more basic, like strings theory? Is that just a mathematical construct and you can't ever prove it in a machine?
Yeah, so the string theory is constructed in order to describe all of it in a more fundamental, all of the particles that we see and interactions in a more fundamental way. Okay, but currently there are so few predictions that you can actually test the string theory that it's very difficult to say that whether any of that is really correct. I mean, theoretically, yes, it could be, but for the moment, we're not really there to actually tell you that this is the way it works and this is the string theory that it has to be. There was a hope at some point that we would actually be able to do this in a purely intellectual way, that you would actually be able to get to that one theory that's correct. But I believe that's not the consensus these days, but I'm not an expert.
Would this help you come up with a theory of everything where you unite magnetism and gravity?
Yeah. So that's the long-term aim of particle physics, is so the thing that we don't actually understand is gravity. This kind of force carrier type thing that I talked about, that doesn't work very well for gravity, and that's one of the problems of particle physics that we haven't figured out.
All right. I want to thank everybody for coming out this evening. It's great to see interest in the fundamental sciences, and it's great to see the community coming out to Argonne and learning more about what we're doing across the world. Let's thank Rik very much, and actually I want to thank everybody who came out as well.